Good morning, Pros. Okay, this is Group 10, and today we'll be going through our model. So, in our model, what we have done is that we are predicting solar energy output so as to achieve better planning and improve efficiency, improve energy storage management. For those people who need it. And in this case, is a manager of a solar power plant in India. Okay, how we did this is that we took into account two data sets. One is plant one generation data and plant one weather sensor data. Okay, these two data sets are shown here, and these are the heads of both, and these are the columns of these data sets. Okay, which will be used later to achieve our desired output in our model.
Okay, so since we have gone through the columns, we can start with cleaning and analyzing the data by looking at the date and time column and standardizing it for both the gen and weather data frames that we just extracted from the CSV files. Then we can't merge directly because uh, of the existence of the 21 rows for each inverters. So we sum all the inverters into one total aggregate solar power plant, DC power and EC power. Then merge the data set, both the weather and generation data set on date and time. So we'll have a consistent 3000 rows as seen here. Now, what do we take away from the distributions? So it's very tail heavy, which means it's leaning towards zero, and it's recorded from 15th May to 17th June for every 15 minutes, and hence there are 3000 data points. Plant ID is constant, and the model temperature spans over from 20 to 30 degrees Celsius, which makes it general for any Asian countries, so it can be used anytime. Now, how do we drop? So we just drop the redundant columns like plant ID, source key, daily, total use we're not using. Then we just visualize to validate our assumptions, which were the zero part, right? So as you can see, the histograms were kind of tail heavy, which means they were leaning more towards the zero paths. We also plot scatter plots to see how DC power works against the time, and you can see that it's very centered towards the daytime and zero in the nighttime, which is because of the irradiation being high in the daytime and zero in the nighttime, which proves their relationship, along with the fact that we have to remove the zero parts of the dataset to predict accurately during the daytime. Now we move on to scatter matrix plots to just check the relationship and how strongly they affect each other. And we figure out that irradiation and AC power are quite strongly related, and they are mostly similar relationship between model temperature and ambient temperature, which with more data engineering can uh, have the potential to be very good features. So we plot the correlation heat map. Then we find that the features that we want to give out are model temperature, irradiation, ambient temperature, and sign and cost time. Why sign and cost time? Because it captures the cyclical patterns in the output at the same time during the day. Okay, now we extract a target and test features, and we train test pattern 70 and 30. Then we normalize it, standard stuff according to the cohort class problems, and then we prepare the feature matrix, and we move on to building the model.
Okay, so to build the model, we just first initialize our parameters and train a typical linear regression model using gradient descent, and the functions used were just taken from the problem set to fit our use case. So applying all of this, we now get beta. We now like to analyze our beta. So irradiation is actually one of the most dominant as expected due to its strong linear relationship with AC power. Temperature is also significant, and the other three features have a negative coefficient and are less significant. Contrary to our previous visualization, the coefficient of ambient temperature is negative. One possible reason is that the feature are somewhat correlated, leading to unstable coefficients. To ensure that our model was learning at a correct rate, we then check our gradient descent coverage. We do this by plotting our J storage, and we can see that from this graph that our model is learning really fast, and it starts to actually have diminishing returns from about 3 to 400 iterations onwards, and the rate of growth is actually negligent from here on. So with this, we are now able to evaluate our model using mathematical functions such as RSME, R-square score, and adjusted R-square. These metrics help to evaluate both the accuracy and generalizability of our model. So evaluating our model, we get a RSME of 1132, indicating low average prediction error in our AC power output, R-square score of 0.971, and an adjusted R-square score of 0.971. This model shows very strong predictive performance with high R-square score of 0.97 and a low RSME, indicating it captures most of our variance in AC power. Now, in order to improve our model, we like to explore the dataset more, and we realize through our residual patterns that most of our predictions have low residuals, but certain mid-range power outputs from 12 to 13 kilowatts show large error. And this indicates more limitations in capturing complex behavior within these ranges. So one of our ideas to improve was to explore nonlinear models such as polynomial regression. So to do this, we used the grid search with k-fold cross-validation, and we tested the polynomial degree from 1 to 5 to evaluate how well it will do, increasing complexity. So doing our grid search, we actually accounted for and decided that the best degree would be 3, and after tuning the parameters, we then train our better model using this model, and we get these statistics over here. So while it's not a crazy increase, we do have an increased R-square score and a lower RSME, showing that the polynomial regression has indeed improved the model, although not that much. So you can see that this is our predicted, and it shows a really good fit. So we'll now show you the Streamlit web app.
Okay, so this is the web app that we have created. So Mr. Rajesh Kumar can just come here and then input his temperature values and just click on predict, and will predict close to accurate AC power that will be generated by the power plant on that temperature and irradiation. Next, if he wants to batch predict for multiple days, he can just go here, browse files, click on any file he wants to dump with the sensors in, and just get his AC power predicted. Yeah, that's all. Thank you so much. Thank you so much for your time.